Let us talk about this problem. We are given a binary tree. We need to find out maximum width in this binary tree. For example, if you see this binary tree, width of this level or number of nodes at this level is 1. Number of nodes at this level is 2. Here we have 3 nodes and here we have 1 node. So if I see and find the maximum of all the levels, I'll have 3 nodes at this level. So my output is 3. If we see this binary tree, we have 1 node at every level, so output is 1. If we see this binary tree, we have 1 node, 2 node and 4 nodes at this level, so the output is 4. For an empty binary tree, our output is going to be 0. There are no nodes at any level. Now please pause this video and write a function that takes root of a binary tree and returns an integer value which is maximum width of the binary tree. One hint for you to solve the problem, you can use level order traversal line by line logic to find the maximum width of binary tree. You may pause the video again and now try writing the solution. The idea of solution is to push all the levels one by one into the queue, and after pushing every level, get the queue size and check if the current queue size is greater than current result. If queue.size is greater, then update the result. Finally, we have the maximum width. So if I see this tree, we'll first push 10 into the queue, which is one level. Then we'll push 20, 30 into the queue, which is the next level. Then we'll push 40, 50, 60 into the queue, which is the next level. And after pushing every level, we'll check if the current queue size is greater than the current result or not. If the current queue size is greater, we update the result. Now, how do we ensure that we are going to push all the levels one by one into the queue? We have talked about it in the level order traversal line by line method 2 video. Let's see Java and C++ codes here. What are we doing in these codes? We are first creating a queue. Then we are pushing root, which is first level. We are initializing the result as 0. If your tree is empty, then your result will be 0. Otherwise, it will definitely be at least 1. So we initialize it as 0. After initializing this result, we do the level order traversal loop. And inside this loop, we first get the queue size, which is the size of current level present into the queue. Now what we do, we update this current size with the result. If it is greater, then we update the result. And after that, we traverse through all the nodes of current level which are there in the queue. For example, when 10 is there in the queue, we'll traverse through 10. And next time, when 20, 30 are into the queue, we'll traverse 20 and 30. So when we traverse all the nodes of current level, we enqueue the nodes of next level, right? So once your last node of current level is traversed, your next level is completely there into the queue. So your job is simple. You are pushing nodes level by level into the queue, and every time you are checking if the size of current level is greater than result or not. If it is greater, you update the result. At the end, you need to return the result. So there is a new line has to be added, return result. That will return the result at the end. Similarly here, we need to add a line, return result, which is our final result of level order traversal. Now, what is the time complexity of the solution? This solution traverses every node exactly once. When we say traverses, it means every node goes into the queue exactly once and comes out of the queue exactly once. So we are doing constant amount of work for every node. So the time complexity is big O of n, where n is the number of nodes in the tree, or we can say theta n if we want to be more precise, because we are going to do exactly theta n work, exactly constant work for every node. Now, how much auxiliary space this solution requires? It requires theta of maximum width of tree as auxiliary space, because at any moment you will have a level into the tree, and whatever is the maximum level, that many nodes have to be there into the queue at most. So time complexity is theta n, auxiliary space theta of width, and if we want to write down auxiliary space in terms of n, we can say big O of n, because width can be almost n by 2 in a perfect binary tree.